example, we've got a 3 by 3 matrix, -1, -2, -2, 1, 2, 1, and -1, -1, 0. And we want to find the eigenvalues and eigenvectors of this matrix. So this one's going to be quite a bit messier algebraically than the previous example, but the principles are still exactly the same. So let me walk you through that. Remember, we want to figure out A minus Ri. Now, Ri means you would have R's down the main diagonal. So what we're going to do is we're going to subtract R's from the main diagonal. So I'm going to go ahead and write those in. A minus Ri on the original matrix would be -1 minus R, 2 minus R, and 0 minus R. And now we've got to take the determinant of that matrix. I'm going to highlight things in green so it doesn't get too messy here. But it's going to be a little bit complicated because remember, for a determinant of a 3 by 3 matrix, you've got 3 forward diagonals and then 3 back diagonals. So it does get a little messy. We have plus on each of the forward diagonals, minus on each of the back diagonals. So let's go ahead and figure each one of those out. The first main diagonal is -1, -1 minus R, times 2 minus R, times 0 minus R, which is just minus R. And now the next diagonal is -2 times 1 times -1. So that gives us -2 times 1 times -1. I'm sort of wrapping around to the other side. Maybe I'll go ahead and write those columns to make that a little more obvious. So on that first column, I've got -1 minus R, 1, and -1. The second column, I've got -2, 2 minus R, and -1. And so if I look at that second column, that second diagonal here, that's +2. So that gives me a 2 there. And so I'll put a +2 here. That third column, or that third diagonal, again gives me a +2. And now I'm going to work the back diagonals. So that back diagonal right there, remember it's negative, and I have 2 other negatives, so the whole thing is negative. So -2 times 2 minus R. That's that first back diagonal. That second back diagonal, again, remember that each one of these is negative, or at least we're going to multiply it by -1 and then see what it comes out to be. So that second back diagonal is -1 minus R times -1, and then there's another negative, so it's plus -1 minus R. And that third back diagonal is -2 times 1 times -R. So there's 2 negatives in there, and then there's another negative because it's a back diagonal. So the whole thing is -2, actually positive, or -2 times R. Because there's a negative, and there's a negative. So you put them all together, you get 3 negatives, and it simplifies down to a single -2R. So we get a fairly complicated expression here. Let's expand things out as best we can. This -R, I'm just going to write it as -R here. And now I'm going to multiply these 2 terms together. So I see I've got -R is R squared. -2R plus R is -R. And then -1 times 2 is -2. And now let me collect some terms here. I see I've got a +4. That's +2 plus 2. -2 times 2, so -4. Plus 2R. And then -1 minus R minus 2R. And again, if I multiply this -R through, I'll see I'll have -R cubed plus R squared plus 2R. And let me collect some terms here. The +4 minus 4 cancels. I see I've got a -1. And 2R minus 2R cancel, but I still have a -R here. And so if I simplify that all down, I've got -R cubed plus r squared plus 2r minus r is plus r minus 1. And remember, you want to set that equal to 0. We want to find the determinant of a minus ri is equal to 0. So I'm going to multiply this. I'm going to set it equal to 0, and then I'm going to multiply both sides by negative 1. I don't really like having a negative sign on the leading term there. So I'm going to go r cubed minus r squared minus r plus 1. I got that by multiplying both sides by negative 1 there. And that's equal to 0. Now, I'm going to solve this by grouping. I have to somehow factor a cubic polynomial, and it's usually useful to do that by grouping. So I'm going to write this as r cubed minus r squared, and then minus, I'll write this as r minus 1 is equal to 0. I can factor that as r squared times r minus 1 minus r minus 1 is equal to 0. And so I get r squared minus 1 quantity times r minus 1. I'm factoring out r minus 1 is equal to 0. But r squared minus 1, I know I can factor that into r minus 1 times r plus 1. And so when I finally factor this all the way down, I see I have 2 roots of r is equal to 1. And 1 root of r is equal to negative 1. So those are my eigenvalues for my matrix, 1 and negative 1. Now, I still need to go through and find the corresponding eigenvectors of the matrix, and I need to find eigenvectors for each one of those, for r equals 1 and for r equals negative 1. So I'm going to start with r equals 1. Actually, I think I'll start with r equals negative 1. And I'm going to plug that back in to the matrix. I'm going to plug that back into the minus r for each one of these. Now, since r is negative 1, that means I'm adding 1 to each one of those entries. So let me write that out. If I add 1 to each one of those entries, negative 1 plus 1 will give me 0. Then I have negative 2, 1. Now I have main diagonal. 2 plus 1 will give me 3, and 1. Negative 1, 0 plus 1 gives me 1. And so I want to find eigenvectors corresponding to this matrix, which means I have to do row operations on this matrix. I think what I'm going to do is I'm going to bring this third row up to the top, and then I'm going to use that to clear out the other rows. So I'll put 1, 3, 1 on the top row. Switch that down to 0, negative 2, negative 2. And I'm going to use that third row, that 1, 3, 1 row to clear out this negative 1. So I'm going to add 1 copy of the middle row to the bottom row. These are elementary row operations that we learned how to do in linear algebra. So if you're a little rusty on this, got some lectures on linear algebra here on Educator.com. You might want to check those out and just remind yourself how to do elementary row operations. So if I add this 1, 3, 1 to negative 1, 1, what I'm going to get is 0, 2, and 2. So that's already looking a little better. I've created zeros in my first column. Take that one more step. I'm going to get 1, 3, 1 in the first row. And that second row, I can divide by negative 2. I'll get 0, 1, 1. And then I could use that 1, 1 to clear out the bottom row. Actually, I could subtract it away completely and just get 0, 0, 0. And I think I'm going to take it one more step. I'm going to use this 1 to clear away this 3. So I'm going to subtract 3 copies of the second row from the first row. So that'll give me 1, 0. Now I've subtracted 3 copies, so 1, 0, negative 2, 0, 1, 1, and 0, 0, 0. And I want to see what x, y, z would have to be in order to give me 0, 0, 0 there. And so if I look at that, I see that I've got several equations here. I've got x, from the first one, x plus 0y minus 2z is equal to 0. From the second equation, I've got 0x plus y plus z is equal to 0. And I'm going to build my eigenvector. And remember how I said in the previous example, you can sometimes start by just taking the last entry to be 1. And that works this time. So if my z is equal to 1, if z is equal to 1, then y plus z is equal to 0. So y would have to be negative 1. And x minus 2z is equal to 0. X equals 2z, so my x would have to be 2. So I'm going to fill that in, 2, and then my y is negative 1, and my z is 1. Now, if you're uncomfortable with that, if you're not quite sure how I did that, what you can do is you can solve this by free parameters. You just set z to be an arbitrary free parameter t, and then since x minus, well, let me go backwards and say since y plus z is equal to 0, you'll get y is equal to t, negative t, and since x minus 2z is equal to 0, you get x is equal to 2t, and so you'll get xyz is equal to 2t times over negative t over t, and so you could factor out the t, and you just get 2 negative 1, 1 times t. And then if you take t equal 1, you just end up with that same eigenvector that we found by my little trick of just taking the last entry to be 1. So what we've got so far is we found the eigenvalues, negative 1 and 1, and then we found an eigenvector corresponding to one of the eigenvalues for negative 1. We still need to find an eigenvector corresponding to the other eigenvalue, r equals 1, but let me kind of recap what we did here on this slide before we move on and find the eigenvectors corresponding to the other eigenvalue. So I'll go over this in red here because it looks like I've already used up the blue and the green potential. What we first did was we looked at a minus ri. So that meant we subtracted an r on the main diagonal here, and then we found the determinant, which meant this cross-multiplying 3 main diagonals and 3 back diagonals. Remember, the main diagonals, each one of them is going to be plus on the main diagonals, the forward diagonals, and then when you do the back diagonals, each one is going to be negative. So you're multiplying positively all these forward diagonals. That's what we're doing here, and then multiplying with an extra negative factor all these back diagonals. So that gets to be kind of messy, and you have to be very careful not to make a mistake as you work through all those. But it simplifies down. We worked out all the algebra here and simplified it all the way down to r cubed plus r squared plus r minus 1. And then we multiplied everything here by negative 1, both sides by negative 1, in order to get a nice positive coefficient on the r cubed. Then we could group the terms and factor out r minus 1 on each term. So we factored out an r minus 1 by the whole thing, r squared minus 1. That factored down into r plus 1, r minus 1. And so when we looked at the factors, we got a double root at r equals 1 and a single root at r equals negative 1. So those are my two eigenvalues, 1 and negative 1. And then I'm going to find eigenvectors for each one. R equals negative 1. We plug that back into the matrix, which means we're subtracting negative 1 along the main diagonal, which effectively means we're adding 1 on the main diagonal. So that's why we got the 0, 3, 1 on the main diagonal. All the other entries are just the original matrix. And then we're row reducing this according to our rules for linear algebra, and we row reduced it to reduced row echelon form. And then from there, we're trying to solve for x, y, and z. And you can use free parameters the same way you learned in linear algebra, or you can use my little trick of starting with z equals 1 and then working backwards to figure out what x, y, and z, what x and y should be. Either way, you end up with this as the eigenvector and remember, that was just for the eigenvalue r equals negative 1. So we still need to go back and find the eigenvector corresponding to the eigenvalue r equals 1. That's what we're going to do on the next slide. So, oops, I shouldn't have called that a lambda there. That should have been an r. So our eigenvalues are r is 1 and negative 1. And we already found the eigenvectors corresponding to negative 1. So that one was already done on the previous slide. You can go back and check that out if you're just jumping to this part. We still need to find the eigenvectors corresponding to r equals 1. So remember, the way we do that is we plug in a minus ri, which means you subtract r on the main diagonal. So I'll do minus 1 there, minus 1 there, and minus 1 there. And I'll see how that works out. A minus ri is equal to, now negative 1 minus 1 is negative 2, negative 2, negative 2, 1. 2 minus 1 is 1, 1 there. Negative 1, 0 minus 1 is negative 1. And what I see is basically 3 copies of the same row. They're all multiples of 1, 1, 1. So if I pull that 1, 1, 1 up to the top, I can get 1, 1, 1 in the top row, and then I can use that, just multiples of that row, to kill all the other rows. Send all the other rows to 0. And so I'm trying to find vectors x, y, z, so that when I multiply that times x, y, z, I get 0. And all that really tells me is that x plus y plus z is equal to 0. So I really don't have very much information about x, y, and z. I'm going to use my free parameters to solve that. So I'm going to set up z is equal to t. Now my y, I still don't have enough information to solve for y, so I'm going to set up another free parameter, s, there. And then now I can solve for x, because I have x plus y plus z equals 0. That's telling me that x plus s plus t is equal to 0. So my x would be minus s minus t. And so my x, y, z vector is equal to, okay, my x was minus s minus t, and my y was s, and my z was t. What I'd like to do is factor that out, get an s part and a t part. So I'm going to get an s vector, and I'm going to get a t vector. Now my s, I see the coefficients of s are negative 1, 1, and 0. And the coefficients of t here are negative 1. And there's no t in the middle, so 0. And then there's a 1t at the bottom. So the vectors that I get are s times negative 1, 1, 0, and t times negative 1, 0, 1. So my eigenvectors, looks like I have 2 eigenvectors, 2 independent eigenvectors. If I just take different combinations of s's and t's, these are corresponding to the eigenvalue r equals 1. My eigenvectors are negative 1, 1, and 0, and negative 1, 0, and 1. So I'm finally finished with finding eigenvalues and eigenvectors there. But let me recap how we worked all that out. The first thing we did in this problem was on the previous slide, but we started out with a minus ri, and we took its determinant. That was a bit messy. We ended up subtracting r's on the main diagonal and then expanding out a 3 by 3 determinant, which meant multiplying 3 things down the positive diagonal directions, 3 positive diagonal directions, and then 3 negative diagonal directions. So it was quite messy. And we got a cubic polynomial, and then we solved that out. We got r is equal to 1 or negative 1. And then on the previous slide, we plugged r equals negative 1 r equals -1 back in, and we found an eigenvector on the previous slide. So that one worked out okay. And then what we were doing here is we were finding our eigenvectors for r equals 1. So we're plugging in r equals 1 into a minus ri here. So we subtract 1 down the main diagonal. That gives us this matrix. And when you look at this matrix, we really have 3 copies of the same row because they're all multiples of 1, 1, 1. So that means we can use the 1, 1, 1 row to wipe out the other 2 rows, and we just end up with the equation x plus y plus z is equal to 0. Now, that doesn't give us very much information about x, y, and z, so we have to use free parameters to solve it. So we'll start out, we always work backwards from z. I start out with z equals t, then I still can't figure out what y is, so I'll set y equal to s. And then finally, if I know what s and t are, I can solve for x in terms of t and s. X is equal to minus s minus t. And so if I plug those back in, the x was minus s minus t, the y was s, the z was t, so that's what I figured out over here. Plugging those back in. And then I can factor out into an s vector and a t vector. I factored out the coefficients of s here and the coefficients of t here. And so those are 2 independent eigenvectors corresponding to r equals 1. Those are the 2 eigenvectors that I associate with the eigenvalue r equals 1. And so I've found all the eigenvalues and eigenvectors of this matrix. So that's the end of our review of linear algebra lecture here on the Differential Equations series on Educator.com. If that wasn't enough linear algebra to get you completely comfortable with finding eigenvalues and eigenvectors, what you might want to do is go and look at the linear algebra lectures here on Educator.com. You'll find a lot more examples and a lot of this stuff worked out in a lot more detail. What we're going to do in the differential equations lectures is we're going to start using some of these ideas to solve systems of differential equations. So in the next lecture, we'll look at systems of differential equations, we'll write them in matrix form, and then we'll use eigenvalues and eigenvectors to solve them. So that's what we have to look forward to next on Educator.com. My name is Will Murray, and you've been watching the Differential Equation lectures. Thanks a lot for joining us. Bye-bye.